Hello. So, we've discussed the idea of antiderivatives, and in particular, we talked about this idea that there's sort of not an antiderivative, right? There's infinitely many possible antiderivatives. So in this, we're going to try to introduce the idea of the indefinite integral. This is sort of how antiderivatives pop up the most frequently and in sort of the context that they're used the most. So in general, the indefinite integral, it's the notation that we use to represent that class of antiderivatives, right? So the notation that we're actually going to use is this interesting jumble of symbols, this weird sort of elongated, squished looking s with that f of x dx. So let's dive into the actual notation and explain sort of how it works. So here's our indefinite integral. Now that symbol on the left, this represents the fact that we're doing an indefinite integral. So in particular, the thing that we sort of want to keep track of here is the fact that it's just this symbol. There's no like numbers or anything above or below that thing, okay? So this is telling us that we're looking at an indefinite integral, aka the class of antiderivatives of f of x, all possible antiderivatives. The other part of this that is sort of maybe a bit mysterious is this dx at the end. So the dx, this is telling you the variable that you're sort of integrating against is the phrase, which is sort of that variable that you're trying to reverse this process for. So the way you want to think about this notation, the way you want to think about these symbols is kind of like parentheses, okay? There you have the sort of open parentheses, the start of the process, which is this squished long S looking thing. And then the closed parentheses is this dx or whatever variable you're using. So for example, if you had the variable w, it would be dw, right? So it's d and then whatever the variable is. The important part though is that these things come in pairs, just like parentheses. You don't want to have just an open parenthesis with nothing else with it, right? Eventually you should close the parenthesis. Same here. You don't want to have the integral sign without the dx, dw, whatever at the end that tells you when the sort of piece in the middle is done, when you're done writing out the function, okay? All right, so let's look at an example. So let's say we have some function like x cubed. We could take the derivative, get this nice 3x squared. If we wanted to represent all the possible things that we could take the derivative of and get 3x squared, that would be the indefinite integral. We represent that with this, again, weird elongated s thing, the integral sign with that 3x squared, and then that dx as the closing piece, okay? And in particular, as we've sort of seen elsewhere, this thing equals, it is a representative of all of the possibilities, this x cubed plus c, right? So that c is that unknown arbitrary constant. So this represents all possibilities, which we say is equal to this thing, meaning that all the possibilities are x cubed plus some constant. We may not know what that constant is, but it's some constant, okay? All right, so what do we do? So in this video, our goal, right, what we want to do is introduce the notation of the indefinite integral, since we're going to be using this thing a lot. And this, again, like most things, is one of those things it's helpful to have an example to see what we mean. So we went through an example and then sort of explained how this thing relates to antiderivatives. In particular, that this indefinite integral is this way of writing the whole class of things, all possible things, whose derivative is whatever's in there, right? So that is that.